Welcome everyone. My name is Jan Weyler from the University of Bonn, and in this talk I want to present our work about joint plant instance detection and leaf count estimation for in-field plant phenotyping, in which we implemented a vision-based approach to localize crops and weeds in the field and simultaneously estimate for each plant its total leaf count to assess its growth stage. The motivation for our work comes from the areas of precision farming and plant breeding, in which the assessment of the growth stage plays an important role. In the context of precision farming, knowledge about the growth stage is relevant for targeted management actions performed by agricultural robots on the field. For example, certain herbicides and fungicides will be most effective when applied at a certain growth stage. On the other hand, plant breeders are continuously generating new genetic variations of crops to keep the yields high. These variations are then planted and their performance is assessed. A key element to assess the performance and the vegetative development of individual plants is to analyze their growth stage, which can be defined by the BBCH index. This index is mainly defined by the total number of leaves developed at the main stem. Here at the bottom right corner you can see an example of the BBCH index 10 for sugar beet, which developed its first 2 leaves. The index increases as the number of leaves increases as well. Especially in the context of plant breeding, the total number of leaves per plant is often assessed in a manual fashion in the field at a subset of locations. This is not only time-consuming and laborious, but also limited in spatial and temporal resolution. Other vision-based approaches rely on images taken in laboratory settings, where images of individual plants are taken and methods to detect their leaves are applied to count the total number of leaves. However, this data is limited in validity since it's captured in a highly controlled environment in comparison to data from real agricultural fields. In our work, we developed a vision-based model which is applicable to real-world field data acquired by agricultural robots and enables us to localize crops and weeds in the field by predicting their corresponding bounding boxes. At the same time, we detect plant-specific leaf key points, which we associate to individual plants, which allows us finally to estimate the total leaf count at a plant level. First, I want to explain our approach to localize crops and weeds in the field. We use a deep neural network based on the recently proposed CenterNet, which predicts the bounding box of an object by estimating the position of its top left and bottom right corner. This is a single-stage object detection approach, which feeds the input image through a feature pyramid network and predicts 2 heat maps. The first heat map predicts the corner locations of all top left corners. The second heat map estimates the location of all bottom right corners. Each heat map consists of 2 channels encoding crops and weeds, such that all corner locations of crops are in the first channel and all corner locations of weeds are in the second channel. Now, to compute bounding boxes, we project corner points with a high score back to the input image. However, these locations are rather coarse, since the resolution of the heat maps is lower than the input image. Therefore, we additionally add offsets in X and Y direction, which we apply to these corner locations and refine their locations to compute more tight bounding boxes. Computing bounding boxes from corner points is a non-trivial task, since you can connect each top left corner to each bottom right corner, which would lead to a high rate of false positive predictions. Instead, we need to find a way to associate top left corners and bottom right corners which belong to the same object. For this purpose, we additionally predict embeddings, which serve as feature descriptors. The network is trained with the objective of small distances between corner embeddings which belong to the same object. For example, given the prediction of the top left corner prediction, we select its corresponding embedding and compute the L1 distance to all bottom right corner embeddings and assign it to its nearest neighbor. This gives us the first bounding box. We do the same for all remaining corner locations to get the bounding boxes of all plants on the field. However, qualitative results show a high rate of false positive predictions, since the strong visual patterns inside a bounding box are not exploited by just predicting corners. For this reason, we additionally predict a heat map of centers. This heat map contains the center points of each bounding box. As shown before, we select center points with high confidence scores and project them back to the input image. Next, we assign each bounding box with a scale-aware center region. If the center region does not contain a predicted center point, we discard this bounding box. Otherwise, we keep it. By this approach, we can detect all crops and weeds on the field by estimating their bounding boxes. Next, I would like to introduce our approach to predict the total leaf count for each previously detected plant. Here, we apply a similar approach to the detection of corner points by predicting an additional heat map which estimates leaf key points. Again, leaf key points of crops and weeds are encoded in different channels. During training of the network, we first create a weight map W with unnormalized isotropic 2D Gaussians at each ground truth leaf key point position, which stores a value of 1 at the ground truth position and lower values which are close by the ground truth position. Finally, we apply a sigmoid activation function to the predicted heat maps and compute a loss as a variant of focal loss, in which the previously defined weight map reduces the penalty if the network predicts a leaf key point at a position which is close by but not exactly at the ground truth position. Thus, we argue that those predictions can still predict a valid leaf key point, since the exact position of the leaf key points is not necessary for the task of counting. Here on the right hand side, you can see how the network is training over multiple epochs and how it's getting more and more confident about the position of leaf key points. After the network is trained, we can project leaf key points with a high confidence score back to the input image. Now, to count the total number of leaves, a simple approach is to just count the number of leaf key points within a bounding box. However, this method fails in case of overlapping plants, leading to overcounting the total number of leaves. Instead, we want to discard leaves if they belong to a different plant. This brings me to the last step of our approach. In addition to the heat maps, we predict embeddings for each leaf key point, which again serves as a feature descriptor. We train the network with the objective of small distances between all embeddings which belong to the same instance, shown by identical colors, and large distances between embeddings of different instances. To achieve this, we define a clustering loss function for training which has two objectives. First, we minimize the squared distance between leaf key points and corner embeddings which belong to the same instance. Second, we increase the distance between leaf key points and corner embeddings which belong to different instances. This push force is hinged. That means it's only active up to a certain distance, denoted by delta. In the same way, we also increase the distance between all leaf key points which belong to different instances. By minimizing those objectives, all embeddings of the same instance are closer to each other than embeddings of different instances. Thus, we can associate them by distance. At inference time, we apply a simple post-processing procedure to associate each leaf key point to its corresponding plant. First, we remove redundant predictions by applying a non-maximum suppression on the heat maps. We apply a max pooling operation with a kernel size of 3 by 3 on top of the produced heat maps, and keep only those key points whose value is identical to the original value. Therefore, we remove redundant predictions. Finally, we select the top n predictions by score and also extract their corresponding leaf key point embeddings. Finally, to match a leaf key point to a single plant, we refer to the set of previously defined bounding boxes and their corresponding corner embeddings. We assign a leaf key point embedding to its closest corner embedding if the distance is less than a predefined threshold and if the predicted leaf key point lies within a bounding box. Thus, we can associate each leaf key point to its corresponding plant, even in case of overlapping plants. Finally, we evaluate the leaf count performance of our method based on the difference in count between the ground truth and the prediction, as well as the absolute difference in count and also the percentage agreement between ground truth and prediction. We also allow an offset of one leaf in the metric percentage agreement plus minus 1 and compare our model with a two-stage mask RCNN approach. Qualitative results show that our model outperforms mask RCNN in all metrics, leading to a more accurate leaf count with a higher precision. In comparison with our approach, mask RCNN is not able to detect all leaf key points of crops nor weeds, and is also less accurate if crops start to overlap. Finally, I would like to give a short summary. We implemented a vision-based model which analyzes the plant development in complex scenes on real agricultural fields by first localizing crops and weeds using a single-stage object detection approach. Simultaneously, we detect plant-specific leaf key points which we associate to individual plants. This enables an automated leaf count estimation for large-scale phenotyping. With that, I thank you for your attention.